There are three approaches to value at risk: analytical, Monte Carlo, and the most popular, historical simulation. What is the historical simulation approach to value at risk? So this is the fifth video in my series on risk foundations. Previously, I answered the question, what is value at risk, and assumed a normal distribution, and that is an approach to evaluate risk that we call parametric VaR if we want to be fancy. We could also call it analytical VaR. That's because we used a smooth function. Here is a different approach. This is called historical simulation approach to value at risk, or VaR. So historical simulation VaR, and in fact this is the basic historical simulation VaR approach, and you may be interested to know that this is probably the most popular approach used by companies, banks at least. So in this case I do need to generate or simulate an historical set of data, but we just want to imagine this is our company's actual profit and loss experience over the last 100 days. So it could be P&L, it could be asset returns, could be portfolio returns. So I'm just assuming 100 days, and then I need a couple of assumptions to randomize. I'm going to assume a mean daily return of 0, which we often do in short periods, and then I'm going to assume a daily volatility of 1%. And so I'm going to use a very typical function here where we randomize the standard normal variable. And so I'm going to get a series of 100 raw returns. Just imagine that these rows here, so I'm only showing the first 7, but they go all the way to 100 days, and I'm plotting that time series, that simulation over here on the left. So you can see that if I rerun it, I'll get a different sample each time. They are IID, they are independent, so we don't expect any pattern. But we just imagine this is our position's actual returns over the last 100 days. Then we'll see that the historical simulation is a simple approach. I do have up here on the right maybe the more familiar histogram, or at least the left side of the body of the histogram where there are only losses. So for example, in this sample here of 100 days raw returns in this column, here is the sorted column so that the worst return floats to the top. This one happens to be negative 3.28%, and on the histogram here it is all by itself here out in the extreme tail, but that's the worst loss. So the histogram, of course, has bins and then the frequency of the losses within each bin. So you can see this is only 100 days, so we get a messy distribution here, but that really is the nature of the historical simulation. Unlike an approach where we're specifying a clean distribution like the normal and it's smooth, the historical simulation uses actual data, which is oftentimes messy, and so it isn't constrained by needing to assume normality. So all we need to do is take the 100 days of raw returns, or whatever is the window here, sort them from worst to best. So here I'm looking at the tail, and here I want to answer the question, for example, what is the 95% VaR? In other words, with 95% confidence, we don't expect the loss to be worse than, and we're answering it just by looking at our historical sample. So using the Excel percentile function is a fine approximation. In the FRM, we're a little more technical, and we follow Kevin Dowd's answer to this question, and it makes a lot of logical, precise sense, I think. And what I mean is that if we're answering the question about the 95% value at risk, then what we're doing here is identifying the 5% tail. See, I have 100 in my overall count, so the 5% tail is cleanly the worst 5 losses. 1, 2, 3, 4, 5, right? We draw it here, and then there's no single correct answer across all users, but at least in the FRM following our approach, Kevin Dowd's, we specify this 95% VaR. The correct answer here would be the 6th worst loss. So it would be a loss of 1.5%. Right here, it's the 6th loss. And you can see I have the unrounded version right here doing a direct lookup. So we don't really use the 5th loss because notice the 5th loss is in the tail, and we want the VaR to be the number that we expect to be exceeded 5% of the time. So you see how logically the VaR is just the value that's right outside the 5% tail. So we would not use the 5th worst. We would use the 6th worst in the 95% VaR case. So for example, in a 99% VaR with 100 losses, we would not use the worst, we would use the 2nd worst. So there's just one other technical item that I want to capture, and that's the other approach we can use, a little bit more sophisticated, and it's shown right here. It's the average of the 5th and the 6th, and this is not necessarily intuitive, so I just have to show it. And under this idea, each of these observations is considered its own random variable where we've observed the center. So if I take the loss of 1.68%, for example, I'm going left to right here. And then the 6th worst loss is negative 1.5%. Right? We've already established that the 95% VaR, the best correct answer here is the 1.50%. But there is the blended approach here as discussed by Linda Allen and also John Hull, and that treats the 1.68 as we're assuming we just happen to observe the center of a random variable. Right, so we just imagine that's what we observe, and it's a random variable itself with 50% to the left and 50% to the right, and then the 1.5 similarly we treat as the observation of a random variable. And so what that means is that in terms of the cumulative weight left to right, when we get to the 1.68% right here, it's actually 4.5% of the cumulative distribution. And so to get the 5%, we actually go here, which is the average of the two values. And that gets us to the, I didn't draw that well, but that gets us cumulatively to the 5% because we've treated each of them as a random value centered on the quantile value that we actually observe. And so that's the logic behind, if we want to be even more sophisticated, treating the 95% VaR in this case as the average of these two values, the 5th and 6th worst. And that's what's listed here as the alternative approach, the average in the 5th and the 6th. So perhaps averaging, like interpolating, was intuitive to you, and you can see here there is a logical justification for that as an alternative approach. But I'll put that in the spreadsheet next to the video if you'd like to download this and take a closer look. Thank you.